Hello.
Hello.
We'll give people a few minutes as usual to join. Hello, John. Nice to meet you.
Good morning.
Oh, shoot.
Can you hear me okay?
Yes.
All right. My audio should be much healthier now.
We can hear you.
Excellent. Hello, John. Nice to meet you.
Same.
I just
How
have to
many
say, yeah,
how many
go ahead.
folks did we get on this call?
How many people do we get? We get anywhere from about 10 to 20,
Great.
depending. So, and it usually takes 5 minutes or so for people to accumulate.
Right. Yeah, I host a weekly call for the National Research Platform that's usually 20 to 30 people. And we help all of our members. It's mostly talk about networking and the infrastructure side, less about the user applications, but it's always exciting.
Oh, very cool. So this, so as you know, from this call gets recorded um, and posted publicly. As almost certainly read, OPI is part of Linux Foundation, so we're administered in conjunction with them, and so like I said, we'll just give people a couple of minutes and we'll get started.
Fabulous. Yeah, I've actually done a presentation to OPI project before for a different group.
Oh, right, that's right. And and we can do this um, where you can do a short presentation and then a long discussion, or a longer presentation with short discussion, or um, just use slides to illustrate topics you think would be valuable to consider with an OPI. Uh, so however you want to handle this is okay with us. We don't have a super heavy uh, process here, except when it comes to the code that actually goes in the GitHub.
Right. Yeah, what kind of time do you want me? Is this an hour, half hour?
So we have till 8 a.m.
Okay,
and we can use the entire. We don't have any other topics for today. You're it, because
fabulous.
you have some I think have some interesting things to say. So why don't we get started? So take it away.
Sure. Okay, I'm John Graham. I'm the lead architect of the National Research Platform, formerly the Pacific Research Platform. And I work for UC San Diego, the San Diego Supercomputer Center. And well, as soon as the Bluefield 2 came out, we started getting into DPU, IPU, and basically anything that could accelerate our workflows. And so I can share a few slide decks that demonstrate how we are using DPUs, FPGAs, and hopefully soon some IPUs and other accelerators. We do a lot of GPU and FPGA, and we're now getting into a lot of CXL and computational storage, and we participate in a lot of international high performance research and education network experiments. Right now, we're all scrambling for SC24, and then not long after OCP 25 in San Francisco. Okay, so this is I'm going to describe the current test bed and the infrastructure that we have, and then I'll land on a recently presented work doing LHC skimming filtering applications using Bluefield 3. It's pretty exciting that our group just released it. Let's see. Anyhow, our research infrastructure this is inside of UCSD. And so we have a UCSD owned 400 gig Arista that's co-located in Scenic Packwave, which is our regional high performance network provider. And to them, currently we have 4 100 gig links into our Oasis 1 and 2, which is a pair of high performance Arista devices. And from there, we connect over to the Fabric Rack 2x400, which Fabric is an ESNet terabit network ring with a whole bunch of campuses like ours connected. We only have 100 gig coming off of our Fabric node, but we have 2x400 to talk to from that rack to all of our other assets. We have a Chameleon rack that we recently stood up. We also have another building that has a whole nother stack of research devices in another building across hall. This is Mayor Hall, our physics, and this is another stack of FPGAs that are coming online soon. Our core infrastructure is a 400 gig AS9516 P4 switch, and then a SN3700. This was donated by NVIDIA many years ago now, part of a Caltech pair. Caltech gave us one of these that NVIDIA gave to them. This one was donated by Arista to UCSD. And so we depend on participation of all of our friends to be able to give us early access to these devices, because sometimes it takes us a year to develop the proposal to purchase these ourselves. And so we do a lot of events with vendors and our partners, and this is one of the ways that we set all this stuff up over wide area networks and then provide services during SC24 and OCP 25. We will be doing demonstrations on the show floors over wide area networks, showing how these systems can be brought up quickly and then centrally managed. So it's all about distributed compute and storage and programmable networks and how you can orchestrate these at a national level, international level when it comes to the workflows. So this is the core of the programmable infrastructure of a Category 1 NSF grant called the PNRP, the Prototype National Research Platform. This is a $20 million award, 10 years of life. It has a stack of composable fabrics, GigIO fabrics APIs that hold a bunch of FPGAs and GPUs, and those can be composed to, currently we're composing them to a bunch of A100 GPU nodes. And so we're attaching 2 FPGAs to most of these, 4 to a couple, And then over here, we're composing 4 A100s to 2 CPU nodes. On the other side of that, they're also plumbed into this high performance 400 gig infrastructure with ConnectX 6 VPIs. So we can do all kinds of storage connections um, we eventually want to be replacing some of these with Bluefields or IPUs or other network accelerators. And we encourage, we have a bring your own resources project program inside of the National Research Platform where we can have universities request specialized equipment be installed in these racks. Like we can swap out devices into these APAs that hold a bunch of PCIe devices that can get composed to any of this. So we have composable PCIe on one side and then composable network on the other. And then this is just kind of a zoom in showing we're expecting these IAM A860M. These are the Agilex M series CXL capable FPGAs, 400 gig connections coming out of these each, and then a bunch of Gen 5 and Gen 4 machines. And then this is showing how they're all stitched into the programmable network fabric. And then this is our U50, the Stratix 10. These are another bitware FPGA, the SmartNICs. So as you can see, we're very much into the SmartNIC paradigm. Mostly at this point, we've invested in the FPGAs, but I'm pushing hard for other IPUs and DPUs. But again, it takes a long time to generate the funding to get these. All these Stratix 10s were donated, by the way. So we do get a lot of donations. This is the wide area research infrastructure that we touch. Here's that same Oasis 1 and 2, our primary Arista core switches, and then our fabric rack. You see the 100 gig link out to the fabric ring, but we have these 4x100 through the UCSD owned device on the LA Scenic Packwave backbone. So we have a bypass. We can actually route, instead of going across fabric, which is only 100 gig, we can go 2x400, 4x100 to get out to any path that we want. And so we create loops off of devices hanging off of our infrastructure inside, and we go out across ESNet, back into New York, across fabric, go here, go down here. We can create multiple loops with different latencies and different QoS and test wide area protocols at speed and on backbones. So it's an experimental programmable research network that is an overlay on the core of the research and education networks. And so this is the example of the combination of all these loops. We have the Gen 4 nodes over here, the Gen 5 nodes over here. These guys are used to make, you stand up an experiment, half of it's on one node, half of it's on the other, and then you just run across the loop, and you're always using the same test equipment to test the performance of the application over the wide area. And it's extremely nice system to have available at the touch of a button. This is the aggregator, the ESNet aggregator, and I'm highlighting that is Caltech on the right and UCSD on the left, and all the other paths out to CERN, GEONT, AMPATH, Hawaii, Guam. So this is a truly wide area programmable network. Through our connections in South America, we can also get to the astronomy sites in Chile and Argentina, and also through to South Africa. And of course, ARNet, we have lots of connections to get the Australian folks in. This is last year's spaghetti monster. All the green boxes are highlighted, uh, and all the green traces are part of the global P4 lab experiments that were executed last year during SE23. The map looks very similar, but all these bright green boxes are Bluefield 2 nodes that participate in the global P4 lab by running free route, sorry, not free router. I've forgotten. Uh, but it has free router
Is it
built
free
into
range route?
it's a global P4 lab uses a wrapper around uh, 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 free router. Anyhow,
So,
they
so
do a P4 emulation on top of the Bluefield ARM. It's not true P4, but it's enough to allow us to all these deployed elements can work with other P4 elements in this wide area P4 experiment. And
is
so
this
there's
a new routed overlay of some kind? So you basically wrap FRR and then essentially can manage specific tunnels for specific experiments
yes,
or research groups?
yeah, we have a layer 2 API, this right here. Basically, this is how we stitch the paths together. We can create, it has an API that we can engage and disengage a previously defined path. And it's using Yang models to actually try to pack the ESNet backbone, but not overpack it. And so you can reserve a slice at a specific time in the future for your experiment to start, or you could just dynamically provision a circuit through this interface and get, 100 gig path from CERN to San Diego.
Ah, okay. So,
And then we do overlay. We put BGP on the endpoints and we run our own BGP routing over the overlay network.
okay. Right. Okay. That makes a lot of sense. I imagine that's the kind of thing you were doing. And, I know why um, physics and astronomy type guys would want that, having been one back in the 90s. Uh,
Right?
and that is very cool. Yeah, yeah, that is very cool because this circuit provisioned overlay that you then use as an underlay to
Yeah.
run a routed service for an experiment is the
Yep.
kind of partitioning that mostly telcos talk about,
Yep.
but doing it for a set of customers in our language, um, sitting on this high speed global backbone with using DPUs is A, beautiful, B, um, interesting, and presumably you would want diversity in those DPUs and
Absolutely.
common APIs.
Absolutely.
Ah,
We have a garden of architectures. We buy two of everything that's shiny. We used to, at least. Our funding has drooped a bit. But yeah, we as soon as the Bluefields came out, we got them. As soon as the FPGAs come out, we got them. They had to be able to run in a data center and not as a, prototype board where you had to hook up wires to. It needed to plug into PCIe slots.
and
So
do you run, so sitting on here, do you carve off a relatively slow network since you don't actually have to move all that beautiful particle and astronomy data across it? Do you carve off a slice of this for experimental purposes and sort of run your tests and your
yeah,
research over that?
yeah, yeah. We've actually been developing. You're gonna love this. It's called Sense. It's ESNet Sense is the API that we're running, and the Sense orchestrator is this. And so our team wrote a Kubernetes operator that knows the Sense API. So now you can fire up a deployment in your Kubernetes cluster, part of the service is some YAML that stands up the two endpoints in the QoS. So literally, I can engage and disengage one of those paths that's already been established by just calling it in the YAML that launches the pod.
Yeah, very cool. Huh.
It's a lot of fun. All right, so this you said telco. Well, we actually operate our own open air interface wide area experiment. We're trying to run our own 5G network. And so we've stood up some static VLANs to go from UCSD to NYU, and we're also using, there's a blue field in the NicerNet backbone. That blue field is connected as if it was an entire campus to the NicerNet backbone in New York. Let's see, it's at the 32 Avenues Americas POP in New York. So it's actually at one of their peering points. So we've positioned these, you'll see all the blue fields. This is a scenic backbone in Seattle, Sunnyvale, LA, ours at UCSD. We have one at the University of Guam, but that's a 10 gig link. The folks at Gorex in Guam offered us a 100 gig upgrade, actually 2x100 upgrade. So we're going to move the Bluefield node from the University of Guam into the peering point at Gorex. And then we have also iGrok Chicago. That is, in fact, Starlight. And then over here, oops, go back here. The NicerNet node. All right, and so these are just a quick overview of the devices that we're using. We're expecting this now. It's been pushed off another, it's Q1 of next year. We have 24 of these, 7 of those. This is one of the uses. ESNet has a service called High Touch, ESNet 6. And what they do is they use their Nokia devices port mirroring function, and then they send that out. They do stripping in payload stripping in the device, and then forward the headers off to. They use U280 FPGAs, and then they're using a precision time protocol and local GPS time references to remark all the headers with additional timing marks so they can do precision jitter measurements. And so they're able, ESNet's actually able to strip every single header off of every single packet running across their backbone in real time, and then analyze that as an event collection. The things that we're most interested in with the Open Programmable Infrastructure project, top one on my list is secure zero-touch provisioning. The ability for us to deploy systems on campuses all around the world and then remotely manage them via IPMI has been a difficult task for the last 10 years. And so having secure ways of accessing and managing from the bare metal up is an absolute necessity for us to securely grow. And so that's why I ran into the Open Programmable Infrastructure project, because we have needs for security. We've been very vigilant and I would say even lucky, but we have to keep on top of that game for sure. The host-based networking is a definite advantage at some of these locations where we're dropping into the backbone. They don't particularly supply a blended fib for an individual host. They want to give you routes. So we have to do our own BGP peering on these Bluefield nodes at these high performance peering points. We also are very interested in software-defined storage and computational storage. So the NVMe over Fabric, SBDK, absolute, I'll show you some results from some of the work that we just presented. P4, as you saw, the P4, Global P4 Lab, were a lot of people in our community still working on P4. And we've heard noise from our friends at Stordis that there's going to be a new piece of hardware supporting P4, switch-based, possibly even 800 gig. So we're keeping our eyes open for anything P4. As far as integration with the Open Programmable Infrastructure Project, I'd love to be able to take your POC lab. You've got Docker Compose workflows that I would like to be able to convert to Helm charts. We use Kubernetes for everything. Most of the science and research sites, all the LHC, Fermilab, everybody's, they've drank the Kubernetes Kool-Aid. The other thing we're very interested in, we've heard word that Red Hat is working on DPU operators. I'm sure you guys are also deep into this, but anything to integrate into Kubernetes is beneficial to our entire community. And we just had a call with some friends at University of South Carolina. It turns out they have a couple of E2100 IPUs from Intel, but are struggling to figure out how to get the development environment and the P4 compiler license and all the other things set up so they can actually use it. And so we've figured that out. We've slogged through all the Intel memberships we need to do. I've gotten permission from the campus to push buttons on websites. And we now have the P4, Intel P4 compiler running securely in our GitLab CI/CD engine in our self-hosted GitLab. So at this point, you can put up a new repo and set up the CI/CD to build the P4 application in a node that has the license, and then return that to the GitLab registry as an artifact. That artifact can be then pushed into the Sonic switch to do our ESNet high touch mirroring function in P4 instead of using hardware mirroring. Or we can do the P4 build for the FPGA. The ESNet SmartNIC supports P4 inside of its stack. And so for SC24, we're doing SRv6 microSID experiment in FPGAs using a U280 at Starlight on the Fabric rack, plumbed across Fabric using the Sense API, out to facility ports at UCSD, over to our rack of U55C FPGAs, where we ported the ESNet SmartNIC to the U55C. And additionally, Sienna Group has their own mobile Fabric rack, and they're doing an SC24 demonstration. They have an SN1000 SmartNIC from Xilinx. We're pretty close to porting everything except P4 to that for the ESNet SmartNIC. And so we'll be demonstrating an older version, SN1000, that's running in a mobile rack at SC24. I also own two of those. One of those we're shipping off to Ampath in Miami, and that'll be connected in their Equinox data center at 2 by 100 gig. And yeah, so we'll have a 4-site topology that we're going to be doing a SRv6 microSID experiment coming very soon. Let's see, I think that's it for this slide deck. I'm going to pull up, let's see, is there anything? Yeah, so I talked a bit about the ORAN testbed. Let me just go through this real quick. This is the prototype national research platform. This was the category 1 award that dropped a whole bunch of high-end 64-bit GPUs and FPGAs into UC San Diego, and then 144 A10s at University of Nebraska-Lincoln, another 144 A10s at MGH-PCC. And then all these Internet 2 bubbles is where we deposited cache nodes. So NVMe caches, we want the data to be within 500 miles of any campus. And so we have our own content delivery network overlay on the backbone. Internet 2 is providing, actually they're doing a hardware upgrade on their own dollar. They provided some older machines, and they got such good utilization that they're deciding to grow their commitment to the National Research Platform. This is also National Research Platform hosts the Open Science Grid and the Open Science Data Federation. Frank Werthwein, my boss, is actually the PI of that also. So it turns out that it's easier to deploy other national scale assets on the National Research Platform because it's Kubernetes and federated identity framework. So here's the ORAN testbed. We work with ESNet in Berkeley. They have a 5G, 6G testbed, and NYU is, of course, part of the NSF 5G, 6G. These are some of the maps that show the connections over the wide areas. Yeah. Here's the path. We have multiple paths that we engineered a couple of years ago now to get into the NYU 5G lab. So all of this now is been converted from static paths into dynamic paths. And so, but we can still add universities that are outliers that don't have all the network automation in place. We can just drag them back. Like for instance, NYU did not have the open NSA or any NSI controlled elements. We terminated them at Scenic LA, and then we automated everything as a virtual circuit across there. So that, you know, it just looks weird on the map, but it can plug a campus in quickly. These are just some of the racks of equipment that we have. These are 2 G-Node Bs that we built and delivered, one to NYU. And this is all, again, Kubernetes deployed, open air interface stack. We can also run SRS ran. All of these new 5G, 6G ORAN stacks have Kubernetes Helm chart deployments. So we can easily deploy this on a national scale programmable layer 2 path network. So we can create external data network paths between sites, between research experiments, and do interoperability studies. Yeah, so this is the LBL Firecell stuff. And this is our stack, kind of shows the Sense Auto goal, providing the external data network layers. And we also have FPGAs in our G-Node Bs. We wanted to offload as much to FPGAs as possible, reducing the power needs and also giving us the ability to time slice. These USRP radios can do 1 nanosecond time slicing if you provide a White Rabbit network time source. And so we're trying to push the envelope on these devices. We have a few of these little Raspberry Pi 5G IoT devices we're working with for kind of the mobile component for wearable augmented reality 5G uplink. We have some HoloLenses and Apple stuff, Apple Vision Pro, and we're very much into the digital twin representation of everything that you've seen. So we've been working for several years on Unreal Engine digital twins, and recently I've been digging into the Omniverse digital twin. They have the Omniverse aerial digital twin that we are interested in integrating into our resources. We've already got the Omniverse farm deployed in Kubernetes that they were nice enough to provide that. And I've got Omniverse enterprise licenses for doing their full stack enterprise, scaling up all kinds of um, just classical digital twin for manufacturing. But we want to do real-time network digital twin where we uh, assimilate all the real-time metadata into the live representation and visualization. Yep, let's see, get out of this one. And yeah, this is part of the multi-domain. This is again showing the fabric network, but this has a overlay of all the facility ports, and highlighting are all the 5G and 6G resources. So we've got Cosmos at Rutgers, UCSD, Cosmos at New York, Chameleon TAC, and the Utah Cloud Lab Power. And so we can instantly make cross connections over to these cross the paths that already exist. And let's see. Yeah, here's Omniverse digital twin. We're just developing. We can run the Omniverse digital twin distributed across nodes on the National Research Platform. So if you're trying to simulate latency, instead of just faking it, you can do pod placement. So you need something running in CERN. We can place a pod in CERN to simulate your LHC workflow and still do QoS without, interrupting the other guys. I think the last thing, I think this was just presented at CHEP in Poland. Let's see, what's this? This is the team I work with, Diego Davila, Ashe Aurora, Frank Wertheim. He's the director of the San Diego Supercomputer and my direct boss. So this is a paper that they just presented, and I'm not going to go through the whole thing, but they do a thing called data skimming. And so for the analysis stack, they're opening up files and ripping through them to figuring out what they need, filtering them, and then what they've been doing, which you guys are going to be interested in, is kind of just DPU background. You guys know that. Yes, so accelerating LHC filtering, near data computational model. So they want to take advantage. And so here's the skimming process. They fetch baskets, they decompress, they deserialize. Optimize skimming.
So, I apologize if I missed it. A basket is like a opaque blob of data,
Yeah,
or
yeah. LHC stores, they might be using HDF5 in this case. I'm not sure if they call it out in this board.
oh,
It's
this
probably,
is LHC, the LHC collider data.
yeah. Yeah, Frank is the lead LHC yeah, for use for the Western region. We're one of the distribution sites, and Frank and his team consume 50% of my work.
Yeah, 50% of your resources,
And
undoubtedly.
Caltech is other partners, and not
Yeah.
just on the science side, but on the network side.
Oh,
We do,
absolutely, absolutely. I get. Yeah. Okay. So a basket is a container of data, an
Yeah,
opaque container of data that has
yeah,
internal structure that you don't need to know about
yes.
to do the
HDF
math.
has got layers in it. And
To
so
do
you have to rip through the layers to get the energy level of the particle that you were looking for. And then if
yeah.
it's got a missing float value, you have to reach up to a different level, reduce that data, and re-inject it. And so this is a computational storage
Ah, now I
workflow.
know exactly what you're talking about because we used to call this tag containers at Slack
Okay.
for a bar experiment.
Oh,
So
okay.
yeah, we used to call these tag containers and we shipped them around opaque in just this way. Perfect. Okay,
Yep.
now I fully understand. Okay, this is excellent. Beautiful. Keep going.
This is
I like
still
it.
no DPU involvement. So
Yeah.
they've been optimizing the process, and so they're changing the way they do stuff. But now they kind of describing what the DPU is. We're using an xroot D server, which is basically HTTPS. And so we're calling that and then filtering the result and then spitting it out to the client, reducing the amount of network bandwidth we need to consume for each client. So classically, they're sending the whole doggone blob, and then the client has to do a lot of the work. Look at the performance improvement. Yeah, we need these.
Seriously?
Seriously.
Man, I wish I could replicate this a whole bunch of other places. We'd have, 2,000 people in OPI beating down the door to
Well,
make
it's
it real.
just the functions in the DPU fit the workflow,
Yeah, I, lovely result. This is
right?
truly interesting.
Here's the limitations. We need bigger DPUs. Where's the 800 gig ones with 128 gig of memory and 64 cores?
Yeah, you need a yeah,
Liquid cool.
you need a 1 nanometer process with
Right.
so it takes no
But
power either.
yeah, but we can scale horizontally. We can just add more DPUs. And just they have some background slides trying to educate their own community about these things. And this is all, this is a public URL, so I can share this right now. Let's actually, if I can get the Zoom controls out of the way.
Yeah, I mean, you can send that after to just
Gotcha.
uh, to the Slack channel.
All right, so I'm just going to stop sharing here, and I think it's time for questions. Is that an enough?
No, that was a great intro. Yeah, I'll open the floor to people who have questions or thoughts. Maybe you want to put up the slide where you were talking about, again, where you were talking about possible OPI collaboration.
Oh yeah. Let's see.
Maybe that's a thing to have as our visual aid. Um,
Sure.
while I open the floor.
Which deck
It,
was that?
it was the first deck you were presenting, like 16, 16.
Right
Uh,
there.
yeah, that was it. That was the guy. Um, and maybe we could just have this as a visual aid or to prompt questions. Okay, I'm gonna open it up to the floor. I could have I could fill the last 16 minutes, but um, uh, I'd rather get a wider set of views. And then you're going to be at Supercompute, John?
I physically am not, virtually for sure.
Okay.
I'm
Um,
trying to build a house right now, and
um,
I'm having disagreements with all my contractors about, permits and laws and reality.
reality. All right. All right. Question. Anyone? Discussion points, questions, thoughts about this? Okay. So let me ask a leading question
Sure.
uh, to kick this off. So this set of collaboration interests, would you want sort of okay, if we gave you these things piecemeal, in other words, each is sort of a separate little thing that you interacted with, but we made these, or at least a subset of these, and maybe the whole list, run across all the DPUs, but we didn't have this, nice, well-defined application package. For your purposes, would that be okay or not so good?
We can integrate anything. We use Ansible playbooks for automation and yeah,
Yeah, because again, we have a secure ZTP that'll
yep,
run across. We have some SBDK for storage
yep,
that'll run across.
yep.
Um, P4 is an interesting one because not all DPUs support
Native.
P4 in the same way.
Yeah, it doesn't matter. We can still put a container on the DPU that does P4. That's what we're doing.
Okay. Um, for the lab, um, we've got, so I don't know, Mark or Murcia, what do you guys think on the lab side in this notion of um, Helm charts for our POC lab, and then maybe hooking into part of the um, test overlay network to try some of these things out, in our lab, hooked to all of John's infrastructure.
Yeah, for the test that I have, shouldn't be hard to do with Helm chart.
Yeah.
Say that again. I didn't quite catch it.
For the existing cases that we have, to also do Helm chart will not be very difficult.
Yeah, I didn't think so. Yeah, I tried to do a compose convert on the Docker compose files, but it versions issues or something was complaining. But yeah, it should be fairly easy to make them work as a Helm chart. I can also give you some pointers on um, making your Helm charts more universally acceptable to multiple bare metal clusters. The need for deploying in different clouds is different than on bare metal. We have stricter requirements for pod deployments. We require you set your requests and limits for each container. We don't want people just, over scaling sometimes. We get out of memory errors and other things start falling apart. So we restrict things and we can give you feedback on your Helm charts.
Yeah. Uh, Other questions or discussion on those points? Somebody? Okay. On the Doka HBN host space, the host space networking stuff,
Yes.
and BGP peering and the DPU topic. If we would the desire there to have the equivalent of the Doka HBN across um, all the families and flavors of DPU so that you integrate the same way? Or is it that you would replace the Doka HBN with a common one that effectively did the same thing so you could get that cross-platform operation?
Right.
What are your
Cross-platform would be best.
okay.
Even setting up a gRPC service inside that we could talk to for doing a common API would be fine. So you could spawn a container that did the translation on the node and answered to gRPC in a common API. That's we use Sonic switches. Our Edge Core 400 gig it's running Sonic Enterprise, and to send P4 applications to that is a gRPC service. I can slam a P4 app and it goes live instantly, and it's all integrated in our CI/CD. So we have version control on P4 uploading into the switch. The same thing could be done at the NIC level. I want to be able to send flows through GNMI, GNOI commands into the NIC. And telemetry is critical.
Okay, so you want the DPU, IPU, the NIC to look like a switch from the outside, but not be a switch on the inside. Is that
No,
what
we want it to be a BGP pairing point on the
Yeah,
inside.
right. So it looks like a switch from the outside. In other words, you're talking to a BGP service
Yeah.
sitting in there, but the packet forwarding is what I would call NIC-like. In other words, it's not doing uh, DP port to DP port forwarding and trying to articulate the ports and all that, but it's got the same BGP service. So the FRR-based BGP service with the switch equivalent API to configure it. And then it can do switch like peering, and it'll claim to be basically a two-port switch, right? One in, one out, a one by
Right.
one switch, where or it'll claim to be a one-up link, a bunch of downlinks to the various containers and or cores and or whatever is running
Right.
inside the OS. How would that exactly work? Because that's an interesting idea. You know, in OPI we had the notion for a while of let's just slam Sonic onto the DPU and
Yeah.
use Sonic to as the core OS of the DPU, put other containers on to do these other jobs like, you know, the basket scraping and that sort of stuff. And then we would get, you know, BGP configuration, we would get Mac, you know, we would get all of the other layer two and layer three services as part of that, taking just the BGP part and pretending it's a switch, but not actually implementing, say, Sonic on there is an interesting approach. What are your thoughts?
Absolutely. Sonic is great. We noticed the Sonic build image tree for the Bluefield a few months back. No documentation anywhere.
Yeah.
But yeah, what we're interested in doing is combining host-based networking and that filtering app that I just showed you that our group is doing. We're going to need more cores to do both of those and telemetry and Blue Man and all the other shiny things that we like. I mean, you guys got some great services. It took me forever to figure out where they were, but you're doing much better on documentation on that stack. But yeah, what we want to do is have sense, the ESNet sense, be able to manage the blue field as if it was the programmable endpoint, usually a switch, top of rack switch in front of the Science DMZ to provide all the network layer 2 terminations, IPv6 configurations, BGP peering, all that. And at the same time, usually the ARM cores for doing the filtering of the data coming in and then transmitting it out to wherever it's going. And so what we're doing is we're using the out of band port, the 1 gig interface, as that um, um, control plane interface. And so what we want to, we should fairly simply be able to have sense talk to whatever API is exposed on that interface and dynamically terminate a layer 2 path into the host.
Yeah. And the your experience of or your reason for DPU versus just buy a server with a bunch of cores and have it do that role is better access to the data that is
Direct. We can offload with I mean ConnectX and Bluefield and IPUs. We can offload a lot of functions. Um, for remote management alone, just being able to attach an NVMe boot device or be able to attach ISO image that we install on the physical local device remotely securely. That's important. Well, we use IPMI to load OS over wide area networks. And so it's slow. You know, we're using a USB emulator through a web browser.
Yeah, okay. So for you, the uh, SmartNIC functions that run on the DPU IPU are
It's
even
offloading.
even at the become a control point for that server node.
Exactly. Exactly.
And it's a control point that's independent. Again, we've made, you probably watched a number of the videos that we put out and Stia put out and so on. And yeah, these points are well understood, and to see that they're valuable in practice is really cool, actually. All
I'm a
right.
pretty good talker, but even I have a hard time talking network security guys at some new campus that wants to attach to us through layer 2 that
Uh,
we need control of their top of rack switch. That's
right.
a hard argument. But if I drop a Bluefield in there, they don't care. I can do everything I need at the host.
So are there any things that you see that need to be fleshed out in some of the APIs that are defined so far, John?
I haven't had a real chance to get up to speed with them.
Okay.
I'm scrambling, getting ready for supercomputing 24.
Okay, no problem. I mean, I
But
think there are things that need to be fleshed out. Not saying that there's not. It's just that if you happen to see anything, just let us know.
well,
Yeah.
I think what I really need to do is I need to get some other vendors' devices in my racks so I'm all about interoperability.
Mm-hmm.
And I do have, like I said, our friends at USC, they have an IPU, so I need to get an IPU in my rack and so I can help them. At this point, it looks like they're just going to attach the node that the IPU is plugged into to the National Research Platform. And that way they can get the Intel compiler access from our infrastructure. And so they can start using them immediately. But that's basically the advantage of our Garden of Architectures. My job is to set up the development environment, the license servers. I got 35 seat Xilinx license tool stack that can run on every one of the nodes anywhere on the planet. Same thing with the Intel stuff. We have to make sure that you have the license with Intel, and then we can enable your namespace that you operate in Kubernetes to access that. And so we still have to manage access for the license technology, depending on the company that we're getting it from. But luckily, we have the framework. We use CI logon federated identity, which means we don't store passwords for anybody anywhere. And they can all create ad hoc groups from industrial partners and university and national labs. They can create namespaces that have members from all of the different users.
Excellent. All right. Well, thank you very much, John. That was excellent discussion, and excellent heads up on all the stuff you guys are doing and why it's valuable. That really, really nice.
And thank you for creating common APIs to yeah, leave a little brain space. I don't have much left here.
Yeah, for sure.
I can't pack anything else in. If I got a one API I can learn, I'm good.
Absolutely. So what we'll do is, we'll chew on this and
Great.
discuss it at our call next week, and and get back to you.
Perfect.
And if you have anyone going to supercompute, a number of us are, from different companies are going to supercompute. I mean, I certainly am, and I'm sure.
Stop by this SDSC booth
Okay.
and also Caltech and Starlight.
Okay. Yeah, I'll stop. I'll definitely stop by all of those, but other people can as well. This will be great.
Yeah.
All right.
Tell them John Graham sent you and
I'll tell him. I'll tell him John sent me. Yep. Yep. And who knows? Maybe I even know one of them. All right. We'll talk to you soon. Thank you very much again.
You bet. Thank you.